In this video, we will handle a special case of floating voltage sources in nodal analysis. This is different from the grounded voltage sources that we handled in the previous video. The circuit shown has four nodes A, B, C, and D. Node A has four elements connected to it. Node B also has four elements, and similarly node C has four elements connected to it as well. Node D is the reference node and also has four elements connected to it. The 440 volt independent voltage source connected between nodes B and C is floating because neither end is connected to the reference node, and this voltage source will require special processing in nodal analysis. Finally, note that the resistor values are given as a conductance with units of Siemens. Before we write any KCL equations for nodal analysis, we note that the independent voltage source is connected between nodes C and B such that the nodal voltage Vc minus Vb will be equal to 440 volts. This equation will be useful in the solution of this circuit. We will begin by writing KCL at node A. The current direction for the current sources is given and we have no choice. For the direction of current through the conductances, we will assume that the currents are leaving node A through the two conductances as shown. And KCL at node A will give us current leaving through the 0.25 Siemens conductance will be 0.25 multiplied by VA minus VC. Current entering through this current source will be minus 3 amperes. Current leaving through the 0.15 Siemens conductance plus 0.15 into VA minus VB. And another current entering node A, which will be given with the minus sign, and it has a value of minus 8 amperes. This must be equal to 0 to satisfy KCL at node A. This is the second equation that will be useful in the analysis of the circuit. Next, we will write KCL at node B. We note that we can write an equation for the current flowing through the current sources or the conductances in terms of nodal voltages and known element values. However, we cannot write a current through the voltage source in terms of these quantities. Therefore, we will introduce a current Ix which flows through the current source in the direction shown, and it follows the passive sign convention for this source. We will write KCL at node B next, and it will give us the current leaving through the current source with a positive sign, and the value of the source is minus 3 amperes. Current leaving through the 0.15 Siemens conductance will be given with a positive sign, and its value will be 0.15 multiplied by VB minus VA. Current leaving through the 0.05 Siemens conductance, 0.05 multiplied by VB, and the current entering from the voltage source, which will be minus Ix, is equal to 0. KCL at C will give us current leaving through the voltage source with a plus sign of a value Ix, current leaving through the 0.25 Siemens conductance, 0.25 into Vc. Current entering from the current source will be given with the minus sign and has a value of 25 amperes. And finally, the current leaving through the 0.25 Siemens conductance at the top of the circuit will be 0.25 into Vc minus Va. And this must be equal to 0 to satisfy KCL. We can add the KCL equations at nodes B and C to get a single equation. And this single equation will give us minus 3 plus 0.15 VB minus VA plus 0.05 VB minus Ix plus Ix plus 0.25 Vc minus 25 plus 0.25 Vc minus Va is equal to 0. Note that we have a minus Ix and a plus Ix in this equation, and we will cancel both of these terms out, and the equation that remains will be called equation 3. The equations 1, 2, and 3 are three equations in three unknowns, VA, VB, and VC. And we can solve all three of these equations to give us the values of VA is equal to minus 62.5 volts, VB is equal to minus 310 volts, and VC is equal to 130 volts. To summarize the processing of a floating voltage source in nodal analysis, we first write an equation that relates the nodal voltages at the two ends of the floating voltage source, which is equation 1. We then write KCL at all nodes that are not connected to the voltage source, which is equation 2. For the floating voltage source, we introduce a new variable, Ix, which is the current flowing through the source. Next, we write KCL equations at both ends of the voltage source, including the Ix current in these equations. Finally, we add the two KCLs written at the two ends of the floating voltage source to eliminate Ix from that equation. If we follow this procedure, we will end up with a number of equations with the same number of unknowns which can be solved for all the nodal voltages. The method for handling a floating voltage source in nodal analysis is to introduce a variable Ix, the current through the voltage source, and then eliminate this variable by writing KCL at both ends of the voltage source. We will analyze the same circuit again and show this time how we can write the equation for the floating voltage source without introducing the current through it as an extra variable that is eliminated. For this, we will introduce the concept of floating voltage sources and supernode. A supernode is a combination of both the nodes on either end of the floating voltage source. For example, the nodes B and C can be combined into one node, which encloses the floating voltage source inside it. And we will write a KCL for this supernode directly without introducing Ix. We will assume that current is leaving through all the conductances out of this supernode in the directions shown. The current direction for the current sources is given and we do not change them. We will write one KCL equation for the nodes B and C together, which will give us that the current leaving through the 0.25 Siemens conductance right at the top of the circuit will be 0.25 multiplied by Vc minus Va. Current entering from the 25 ampere source minus 25. Current leaving through the 0.25 Siemens conductance, 0.25 into Vc. Current leaving through the 0.05 Siemens conductance will be 0.05 into Vb. Current leaving through 0.15 Siemens conductance will be 0.15 into Vb minus Va. And finally, the current leaving through the current source of minus 3 amperes, and this must be equal to 0. This equation is identical to equation 3 written earlier, and we have written it this time without introducing an extra variable through the voltage source. To summarize the concept of a supernode, we combine the two nodes at the end of a floating voltage source and write one KCL equation for the combination. This KCL will give us the same equation as when we introduced a current through the floating voltage source. You can use either one of these methods to handle a floating voltage source. The concept of a supernode is useful to write the KCL equation directly and efficiently.